Hello, I'm Peter Knight and this is number 5 in our series of short geomorphology lectures. As always, I'll talk fast and you can use the pause and rewind buttons to slow me down. The key point arising from the previous lecture is that movement or strain in geomorphic systems stems from the power of driving stresses such as gravity relative to the resisting strength of factors such as friction or cohesion. This relationship is strongly affected by the physical properties of the materials involved, which are themselves strongly affected by environmental conditions such as temperature. In glacier sliding, for example, the driving stress, controlled by weight and gradient, opposes the basal friction, which is increased by glacier weight but can be decreased by basal water pressure. Similar relationships can be identified in other phenomena that involve downhill motion, such as mass movements on hill slopes. Key issues to think about in your reading around this topic include the importance of thresholds and stability, which we discussed in a previous lecture, and the importance of being able to predict geomorphic events, especially hazardous events like landslides, avalanches, and other mass movements. There's plenty of very accessible literature on this topic, including a good introductory web page provided by the USGS, which lists and illustrates some of the main types of mass movements. There are many different types of mass movement, at different scales and moving at different rates. In this course we've been asking big simple questions, so ask yourself whether these events could be predicted. Can the sensitivity of a landscape to this sort of event be assessed? If so, can measures be put in place to prevent mass movements? In this particular location in southern Spain, an engineering solution has been attempted but has evidently failed. What factors do you think might have been miscalculated in this kind of situation? We'll look at some of the basics and you can see if you can work it out. Consider these two examples to begin with: a glacier on the side of Cotopaxi volcano in Ecuador and a hill slope in Almeria in southern Spain. They're features at very different scales and in very different materials moving at different rates, but see how both of them match the theoretical morphology described in the diagram below. So does this suggest that there might be similar processes and similar controlling factors at work? We saw previously that glacier motion could be predicted from knowing the driving stress and the resisting friction, with stress governed by weight, ρgh, and surface gradient, alpha, and with friction governed partly by weight and by basal water pressure. It turns out if you look up equivalent relationships for mass movements, the same terms are involved. The driving stress tau is once again governed by the weight over the contact area and by the gradient. Just the same for mass movements as for glaciers. The resistance in this example given by S is again governed partly by weight and water pressure. In this case it's soil water pressure rather than glacial-hydraulic water pressure, but water plays the same role of lubricating the material and offsetting the overburden pressure or weight. So weight is an important issue in mass movements. The weight on a hill slope can be affected by a wide range of factors including changes in vegetation, construction, or precipitation. Saturating a hill slope with rainfall can have a major effect both on the strength of the materials and also on the weight and hence the stress. Downhill movement is likely when there's no margin of stability, or in other words when the stress is equal to or greater than the strength. This can be reached by increasing the stress or by decreasing the strength. This can be viewed in terms of factors such as long-term weathering or preceding precipitation that predispose a slope to instability, and triggering factors such as an extreme precipitation event that initiate the mass movement. We could also describe these as passive or transient factors, those that build up steadily over long periods, like the gradual thickening of a weathered layer on a slope surface, and those that come and go, like precipitation events. Mass movements become likely when the critical threshold of stability is crossed by any combination of passive and transient events. So we can draw a graph showing stability on the vertical axis against time on the bottom and mark off a critical threshold of instability. Passive factors like slope weathering will lower stability gradually through time. They may eventually reach the critical threshold. Simultaneously, transient events occur, like rainfall events, that in themselves may never be enough to reach the threshold. But in combination with the passive factors, there comes a time when one final straw breaks the camel's back. The threshold is crossed and instability may occur because of a combination of preparatory and triggering factors. So hill slope failure can be caused by a variety of different factors. These can be discussed in the same physical terms as factors controlling other geomorphic phenomena. Prediction of hill slope failure can be based on analysis of driving forces or stresses and a hill slope's stability or strength or resistance to these forces.